Okay, so 8.6 is area where we have more than two intersections. So the first example says the functions f of x is equal to 3x cubed minus x squared minus 10x, and g of x is equal to negative x squared plus 2x. Create boundaries for multiple regions. And so what I like to do first is I like to color code it so I can visually see which graph is belonging to what. So the f of x, the cubic, okay, is this one here. And then g of x is that quadratic. Okay, so notice here compared to the last two notes is we now have multiple intersections. Okay, what happens is that this separates our area. So we're not just having one giant area to calculate. We have to find the individual areas and then eventually add them together. So part A says find x values of the point of intersections and label them from smallest to largest as A, B, and C. Okay, so the intersections we're trying to find is this first one down here, this one right here, and then this one right here. So where both those graphs intersect. Okay, and remember, we can find these intersections by hand. So I'm going to show you how to do this by hand, and then I'll show you how to do it on Desmos. So doing this by hand to find those intersections, this just brings us back to algebra. Okay, so in order to find where two equations intersect, we're going to set these equations equal to each other. So I have 3x cubed minus x squared minus 10x is equal to negative x squared plus 2x. Okay, so the goal here is to get one side equal to 0, and then eventually we're going to factor and then solve for each one. Okay, so the first thing I'm going to do is I'm going to add the negative x squared over to the left side, and what happens is those x squared cancel. Okay, so these are gone. And then I'm going to subtract 2x over to the other side. So I have 3x cubed minus 12x equals 0. Okay, so I can factor this by taking out a GCF of 3x, and I'm left with x squared minus 4 equals 0. And then since x squared minus 4 is a perfect square, I know that I can factor that by doing x minus 2, x plus 2. Okay, so now I have three parts of the factors that I can set, each one separately equal to 0. Okay, so I have 3x equals 0, which means x is equal to 0. Divide both sides by 3. Okay, so that's my first one. And then I have x minus 2 equals 0, so add 2 to the other side. I get x is equal to 2. That's my second intersection. And then my last one, I do x plus 2 equals 0, subtract 2 to the other side, I get x is equal to negative 2, my last intersection. Okay, so it wants me to label these from smallest to largest, so the smallest intersection would be negative 2, then I have 0, and then I have positive 2. So if I was looking at my graph, negative 2 would be over here, A, 0 is here, B, and then positive 2 is over here, C. So since I have the graphs, I could have easily labeled this A, B, and C from smallest to largest because I have that visual, but this is just showing you where those values come from. Okay, part B says set up the integrals that represent the total area of the bounded regions. Okay, so again, since we're looking at two separate bounded regions, we have this one here, and then we have this one over here. Okay, so what we're going to do is we're going to create two integrals. Okay, so the first integral is going to be the bounds from A to B. Okay, so the first integral, and I'm going to, again, keep it color-coded, so this is red because I'm looking at the red area. Okay, so the integral from A to B, so that's negative 2 to 0. And remember, since we're looking at the area between two curves, this is going to be the top function minus the bottom function. So the top function is the function that we highlighted in blue, and that's the cubic, so that's f of x. Okay, and then the bottom function is the green one, okay, which is g of x, so minus g of x. dx. Okay, so that is the area for the very first one, okay, the one that I shaded in red. Okay, now I'm going to add another integral, but instead of doing from a to b, I'm going to look at b to c. So b to c would be 0 to 2. Okay, and now I'm still doing top minus bottom, but now my top function is the top of the green parabola. Okay, so that's g of x. So I'm going to do g of x minus f of x dx. Okay, and then it just wanted me to set it up. That's why I just wrote it in terms of f of x and g of x. I did not have to write out the entirety of the equation. Okay, so another reason we do this way is, let's say we're looking at the graph and we look at all the areas. So this area of the very first one, so that first integral, notice how we have some positive area and then we have some negative area. So ultimately that area is probably going to cancel out, okay, majority of it. And then same right here, we have some positive and then we have some negative area. So if we were to look at the entire bound, so from bound A to bound C, okay, all the way at the other end, we did the integral from -2 to 2, we would end up getting, based on our properties of integration, 0. Okay, and if we were to solve this out, we would not get 0 for the area. So that's why we need to separate it into two separate integrals to represent the two separate areas. Okay. The next part says that you can also use the absolute value to get the same answer. So we can do the integral from -2 to 2 of the absolute value of f of x minus g of x dx. Okay, you can only use this, however, if you have access to Desmos, okay, which most likely you will. Okay, because there's not a way for us to integrate this by hand. Okay, at least not with the knowledge that we have now. Okay. When you do this, notice I did mention that if we had the integral from -2 to 2, the areas could represent 0 because it would cancel out. But since this is the absolute value of that means it's looking at the absolute value of each of the areas. So really there's no negative areas here. So since that's the case, whatever we get for the absolute value of the integration is going to be the exact same answer as if we separated the two integrals. Okay, so if we had to do this without a calculator, we would do this, separate the two integrals. If we had a calculator, then we would use this way, just take the absolute value. Okay. So let's look at number 2. Number 2 says the figure below shows the graph of y is equal to 2 minus 1/2 x squared and the line y is equal to 1 for the interval -2 to 2. Set up the integrals for the sum of the areas of the shaded regions. Okay, so the first thing I would do is I would identify all of the intersections. So the intersection of the line, so I could also color code everything like I did before. So here's the line. Okay, and here's the quadratic. Okay, and all the shaded areas, what they want us to find. So if I'm looking at my intersections, that means I need to find this intersection here. Okay, I need to find, and that's where it crosses the x-axis. I need to find the intersection between the quadratic and the line, and on the other side. So the quadratic and the line, and then also the other x-intercepts. Okay, so notice in our example on number 1, we had 3 intersections, which means we had to create 2 integrals. Now that we have 4 intersections, how many integrals do you think we have to create? 3. Okay, and the 3 integrals are going to be represented by these bounds here. So we have our first integral, and if we want, we can label it again from bound A to bound B. Okay, then we would have bound B to bound C, and then we'd have bound C to bound D. Okay, so again, that's representing 3 different areas that we are going to add together. So I have this one here, this one here, and this one here. Okay, so the first thing we want to do is we need to find those intersections. Okay, so in order to find the intersection, let's go ahead and continue that by hand. We know how to set 2 equations equal to each other and solve for a variable. So we have 1 is equal to 2 minus 1/2 x squared. Okay, so that's setting the line equal to the quadratic, and now I'm solving for x. So I'm going to subtract 2 to the other side, and I get negative 1 is equal to negative 1/2 x squared. Okay, I'm then going to multiply both sides by a negative 2, so that's going to get rid of the negative and cancel out the 1/2. So I get 2 is equal to x squared. And then I'm going to square root both sides. And when I do that, remember I have 2 intersections where it crosses the x-axis. So when I square root a square, what happens is I get plus or minus the answer. So I'm going to have x is equal to plus or minus the square root of 2. Okay, so if I was representing both of those points, that would be B and C. So B is negative square root of 2, and C is positive square root of 2. Okay, where it intersects the x-axis, we can clearly see that that's negative 2, just because we have the visual at the bottom, and then this is positive 2. Okay, and of course, if we did not have the graph, we could graph these equations on Desmos or graph them by hand to have the visual with us. Okay, so let's first do this by hand, and then we'll compare it to our answer on Desmos. Okay, so I need to draw 3 integrals. So starting with the bounds of a to b, I'm going to have negative 2 to negative square roots of 2. Okay, and I'm still doing the top function minus the bottom function. So in this little section here, the top function is the blue line, and the bottom function is the green. So this is going to be 1 minus 2 minus 1/2 x squared dx. So the function for y equals 1 is first, subtracting the other function for y equals 2 minus 1/2 x squared. Okay, and then I'm going to add it to my next integral, and that's going to be the bounds from b to c, so negative square root of 2, positive square root of 2, and then from b to c here, it's still going to be the top function minus the bottom function, so it's the parabola minus the line, and so that's going to be 2 minus 1/2 x squared minus 1, and then dx. And then I have my last integral, which is going to be from bound c to d. So I'm going to do plus square root of 2 to 2. And then again, looking at from c to d, it's the top minus the bottom, so it's going to be the line minus the quadratic. So it's going to be 1 minus 2 minus 1/2 x squared dx. Okay, of course, we could continue, we do this by hand. Okay, or remember, if we were to go to Desmos, okay, and again, this is just having us set up the integrals, not necessarily solve. But you could go on to Desmos and you could take the very first bound, so A, all the way to the last bound, which is D, so negative 2 to 2, and do the absolute value of the line minus the quadratic. So 1 minus 2 minus 1/2 x squared absolute value dx, and you will get the exact same answer as above. So if you want to take a moment and go on Desmos and type both of these in. So type this first equation on Desmos, okay, and then type this equation on Desmos. Okay, and you should notice that you get the exact same answer.